Okay. Okay. Now it's fine. Let's share. And then sit. Okay, so we were going to check some summary also of data acquisition and trigger systems for high energy physics. So just put some reference where I took inspiration, so you can check these lecture programs of CERN for summer students. It's very interesting. And okay, we start with a basic DAQ and trigger system. There are many architectures that depending on the needs of each experiment, they have different requirements for each experiment. So the architectures can vary. And this I can show that this one.
I think you have to click. Try using mouse. Like if you.
Okay. I delete.
Erase all ink on the screen.
Okay. Normal erase. Okay, it's good. Okay. So okay, so but in general, all the systems have common elements. For in data acquisition and trigger are very close related to each other. So yes, so normally for big experiments you have a part that is custom made, and in some cases you have also some commercial electronics to design your system. But normally it's more common to have custom electronics. So the idea is first, when you have a very simple scheme of DAQ and trigger, you have the detector, then you have a delay stage, some pre-trigger stage also, then use some conversion will take the signal from the detectors to convert in something that is readable and to be transmitted through an interface for a computer. And then other part that is trigger. So we will talk about this different type of triggers later on. So this is the most general picture for a DAQ trigger system. Something that is more complex, more complete system. It's that you have. Let's see. So it's lost. There. Where is it? Okay. So we have some monitoring and control system. So where you control the detectors, you control the front end, part of the processing, you can monitor what is happening, and you can configure the system for working. So we have the detectors. The detectors send some trigger signal, and all of them send signals to the front end electronics. Then you have a system which take all the information from the front electronics of all detectors. And here you have the readout network to read out all the information, and event building part, which is this part correlates the information from the detector per event. It produces the information from event to event.
And if you have a continuous readout, that is just, instead of event building, it's just like putting stuff into time slices.
Not always, because the information can come in different times, and you can have different detectors participating in different time frames, let's say.
Yeah, that's right. You use time frames.
Uh-huh.
We just call it time slices.
Or
So-
time
so-
slice, yes,
Yeah,
yes.
so this is the part when if you have continuous readout,
Uh-huh.
you build the time frames.
Yes,
Yes.
yes, you
Because
build.
the event building is much more complex and it usually happens after
Yes.
like readout storage, and after
Uh,
that you do the event building.
Yes, well, this happens. This is normally is different for each system.
Mhm.
So this you can do it later or sooner, or depends how the architecture of your system is constructed. Okay, so but this is just one picture of it. Then first we are going to see triggers. So first we have probably the first trigger. This is in many presentations. I saw this is interesting. So here you can recognize something from here from this circuit. So basically, it's some Geiger trigger there. There's some threshold discriminator, and there is an amplifier, and there is some device that records.
Well, for example, I'm very confused by this.
Uh-huh.
This
Well,
because I don't know what that means. This is a resistor or
yes, resistor.
okay.
But this is very oldish.
Yeah.
Okay, so let's not take that much time. So we have here,
It's a counting chain.
yes, counting chamber. So it's some Geiger maybe, some Geiger. So we have here a resistor. You guess well when you can adjust some the level of trigger, and for triggering you use an audio amplifier. That was like very old. So and then if there is some threshold crossed, you have a relay here, which basically is a mechanical device that switch, and this moves a pen, and you have some paper that is rolling, and when there is some event here, you have some this variation of the movement. And this to detect like counting a number of events. It's very basic. And another one with coincidence, for example, that also very oldish. You have a set of Geiger counters, and you have a control read. Well, these bulbs, very old bulbs, to perform as threshold amplifiers. So when they were crossing a certain threshold, then you get the triple coincidence. That's like
And how is the coincidence registered?
this one. This I don't know. I don't know. I think this was maybe some speaker, like it was tick 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 ticking. But you can, in principle, you can connect anything here. So some relay.
Yeah, I mean like how the logic of and
Mhm.
is done, because you have three signals from three Geiger counters, and how do you logically connect them to register coincidence?
I think here I think here is it works with the current level. So this means that when certain threshold of current, because basically the Geiger counter just is an avalanche.
Mhm.
You have certain level of current, and if this current is equivalent to when you have three.
Like if the current is a sum of three of those,
Yes,
it passes another
passes.
threshold.
Uh-huh.
Oh, okay.
Yeah, I think this is how this is designed.
Okay.
Okay, and then we have well, this is just concept. We have data acquisition with collection and storage the data recorder. From the experiment, we have trigger, which is a set. This is important to understand that this is a set of or a menu of certain conditions that tells to the system that is interesting or not the event. There are different levels. We will see this different level. Um, this can be as simple as one signal from one detector, or can be as complex as partial reconstruction from a collision. So it's like a higher level of trigger. I think we saw that. You can use commercial or custom. So we have this in the other lecture already, so I will skip this one. And we are going to large scale experiment. So custom DAQ and trigger. So because I know about Alice, I will speak as an example as Alice. So here, so we have all the detectors around. So you know more or less. Alice,
Yeah.
right? Okay, we can skip. And oh, what is it? I did. So the basic, well, the picture of how the workflow or the data is flowing here, trigger and data. You have specific detectors with have the feature that are provide trigger signals. So and all the trigger signals are processed by this control trigger processor unit. And then we have the detectors that also sends the rest of the information, not only trigger, but also the more complete information to the readout unit that process the data somehow, and then we have some system that do this another processing of the detector, and also we have the control system which we can use to configure the full environment of Alice. And this is for continuous readout. If you see here, we have the other part. We have other detectors that works in trigger readout. So we have continuous and also trigger readout, because not all the
Yeah, some of them
detectors
are too
have.
slow.
Yes. So and they get the triggers from the CTP. Okay. Okay, well, this is an example. There is also possible for example, other springs that are not colliders, for example, cosmic rays or neutrino detectors. Just to put an example. So, so first, why the trigger is needed? Normally, you can have a large amount of data, especially for collision experiments, for example, and you don't want to store things that are not interesting, or this trash or background. So for this, uh, well, for this you have some electronics with data is the information, but this introduce. Salud.
Sorry.
Salud. Introduce some dead time, because these electronics normally can be very slower than the trigger that the provided trigger. And we have to take this into consideration for the design. And this is really the first type of that data analysis. So which filters the first data, and this is irreversible. So whatever you take with your trigger is all the most you can have. Yes, this is the basic and more effective example. So you have one oscilloscope, you have some trigger detector, you set here some threshold, and then you have the information from the detector that you're studying. But for high energy physics, again, don't want to store all the information. Also, you don't have the capability to save everything, because you can run out of memory. And also, for example, you have to be careful to store rare events that needs like very high rates data volume. So that's one of the goals of triggers. Well, interesting interactions are for permanent storage are stored, some others discard as a background. And the key concept for this is you have some timing, clock readout, dead time, trigger logic, and buffering. So we will see this concept in the next. Here I introduce just because we will be seeing this type of diagrams and concepts in the next slides. So we have the basic gates, which is AND. You know how to read these more or less? Because you have inputs A and B, you have some output. So ANDs basically you have a output of one if the two of them are one, or is just if you have in either of these inputs have one inverted just inversion of the input, and you have another special which NAND, NOR, and XOR. But I will not. This is just inverted AND, inverted OR, and this XOR, one can basically
You have one or the other, not two of them together.
yes. Mhm. And we have multiplexers or the MUX, the multiplexer. So multiplexer, what it does is like a selection of an input. So you have an input here or a set of inputs. It can be also a set of inputs. And you can select either if in the output you have the input A or input B. So depending on this bit. For example, a more complex multiplexer is you have these four inputs possibilities. You have this selector. So and depending on the combination of the selector is 0, 0, you choose A, 0, 1, you choose B, 1, 0, you choose C. So it's like you have a codification of the input that you will select, and this you will have in the output. And this is how it looks like internally. So I don't need to explain in detail, but in the MOOC is the opposite. You have an input and you select to which output you will send the information from the input.
So send only to one, or you
To
can
one of them, yes.
only to one.
Or you can design something that it can send to several, but that is a specific design, but it's possible. And this is an example of a use of the MOOCs. So you have, for example, one input and you have internally in some circuit different gains for an amplifier. So you can select with this the MOOCs different resistor, which means different amplification factors. So instead to have a dial that you tak 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 tak, a mechanical dial, you have some electronic the MOOCs, the multiplexer. Yes. Okay. So first, very basic concepts of trigger. So there, this is called the level 1 trigger. So that is the first stage where every experiment has the trigger. So this means let me see. So the definition of a trigger in the distinction between a trigger or a real system is not well defined. So, okay, yes, there is a mixture of what is the readout system and trigger because they are very too much integrated. And then there is a very typical scintillator coincidence experiment, which is always the first you learn. And the first one is you have just a scintillator with in coincidence, and you have some trigger, which is a counter. So it's a basic counter, and you can scale and have in the middle some other detector that you will read out, and you want the information from it, and you have the scintillator as a trigger for this detector. And also there is like self trigger. This is called self trigger, where you for this you need fast logic and analysis electronics to get the trigger and at the same time to read out. So because you can have a lot of background here, but if you have fast enough electronics, you can do a pre-analysis and discard or select events. Okay, so So this is just a explanation that you when this setup you can have a trigger which has a very good selection with respect to background. This reduces the background, but you can have some constraint of special constraints. So you will maybe interested on this constraint or not. Then for continuous sampling, you don't have this coincidence, but you need to do this fast analysis. What else? Okay, so in this, you basically do the transfer and the performance analysis using um, pattern recognition. That's why you need this fast analysis programming or fast logic. There is no difference between the trigger and readout. And normally in big experiment you have a mixture of these and these things. So in that's you have like you use this different type of trigger, the low level and high level triggers. Okay, so in this architecture you have some latency, or you will want some latency, because normally these detectors are slower than the triggers that you use. No, well, actually, you want very fast trigger that are at least a little bit faster than the detector that you are reading, and well, in this chamber produce some delay, some latency on the time arrival to the processing part. Um, So, and for that, you introduce some delay to trigger, to somehow synchronize the signal from the processor to the processor of the signals. Okay, so that you can do, for example, just implementing a physical cable to do the latency, but also you can do electronically implementing something called a pipelines. With these pipelines is a sort of buffer where you store the information, and later on you match the information. Okay, first the trigger level one is a prompt signal, the fastest signal that indicate that based on the indication of region of interest in synchronous fashion, so just synchronous with the clock of the interactions. And normally it's used to initiate start the readout. And this can be transferred for the next trigger level or permanent storage. Uh, So because of the the current, actually not new, but current Hadron Collider, they have very high rates. It's very common that you can very easily saturate the system because of how fast the interactions occurs, and you can run out of storage capabilities. So, and then because of this, you need some degree of selection to discard a background. The trigger need to separate background from signal. Uh, and the system has to be aware of some physical features in the event. So you design your trigger for that. In some cases, you can even calculate this trigger one, for example, to evaluate lepton content, moment balance, individual momentum, and some in real time. So you need very fast processing capabilities in the electronics to do that, but it's possible. And you can implement data from calorimeters, muon chambers, tracking detectors, and some others. But that will depend on the technology of the detectors, so they can provide. So here use how it looks the different rates expected from different physics phenomena. So you have the total collision, like 2 GHz, is that is everything, and discarding the less as possible background, like minimum bias trigger. Then you have the rate that you expect for big quarks, for W boson, and for HEP boson. So you see that the frequency that you expected this phenomena to happen is varied. So that's why you need good triggers at different levels. So and for that, what it happens is that you design. It can be very complex. For this experiment, it's already very complex trigger design. So you generate your logic depending on a specific patterns that are detected in different layers of the detectors. And one calorimeter you can trigger by jet size, for example, for jets or for muons in some muon chambers, and okay, so this is an example of a table of how the triggers can be designed. No, you have in calorimeters, you can trigger on certain energy obtained, jets from calorimeters. You can trigger on electrons and localized showers or muons that reach some muon chambers, some specific tracks on vertex position, and some coincidence and thresholds variation from the subsistence of centrality, for example.
You are able to determine the vertex position that quickly, so it can be used as a trigger.
Yes, yes. For example, the feed detectors in Alice, they provide vertex position online. So it's but you need this very fast detectors in electronics. So you can achieve this trigger, but it's possible. Mhm. Okay. So clock and readout and triggering. So okay, so normally for this experiment you have a reference clock. In the case of LHC is determined by the radio frequencies of the accelerator, and they are called bunch crossings, in that which are integral multiple periods of the 25 nanoseconds to 25 nanoseconds of that, and where the collision may occur. And for the faster detector, you need some system that can process in this speed that fast, and well, and you can may use some pipelines that is in these multiples to do like to produce some buffers where you store information and you can synchronize later on. Mhm. Okay. Normally, not all the bunches are filled, but then that's why you need the triggers, because not in every position when there are bunches that may collide and there is collision. So you need these trigger detectors to determine when that a collision occurs, and this well, and that is the simple trigger, which is called the minimum bias trigger. Mhm. Okay, so To align when the detector signals, you normally have some pipelines or delay that is produced here. It can be either cables or digital, which are buffers. And this can be divided exactly in this 25 nanoseconds because we know that the clock works in these multiples. And okay, and it is also very important to take into account even the cable lengths from all the detectors because the propagation of the signal in the cable is comparable to the time where the things occurs. In the cable, for example, is 5 nanoseconds per meter, more or less, the speed of the signal. And then you need to align everything. So cut the cables, you have exactly the timing. Okay. I will skip this. It's basically what I say already. So for example, here's an example of the timing for the different detectors in Alice. So for example, here, this detector can provide signals every 25 nanoseconds, and the latency of the time arrival is very short compared with the other rest. For example, TPC has a dead time of, well, for example, feed doesn't have any dead time because it's the fastest, but TPC has like 280 microseconds. So
That's a lot.
yes, it's very slow. This is slower, the slower the detector in Alice.
And does it also have a continuous readout, or do you use some trigger for it?
Yeah, this is all
Also continuous.
continuous, yes.
Mhm.
And the maximum rate is 300 hertz. Then the next one is the inner tracket system, which maximum readout is 100 kilohertz. Well, that will depend also on the type of collision system. But for example, Muon forward tracker is 4 microseconds. And here is, for example, the table how the feed works. So feed has a latency. Is this LM is latency minus, so it's because it's even shorter than in previous runs. So it's 425 nanosecond the latency of the signal arrival to the control trigger processor. And we have other detectors that are slower and for the level 0 trigger, and we have the level 1. We will speak about what it means L0 and L1 later on. Okay, so this is an example how you fine tune some system.
And the LM, L0, and L1 that is specific for Alice, or is that a term like generally used?
No, it's for Alice. The L minus is for Alice.
Okay.
So they didn't know how to name a faster trigger, so they put L minus. Okay, so okay, this is an example of the FDD. How is more or less how you calculate even the cables to match the timing constraints here. For FDD, we didn't match this L minus time because of the distance of the detector is already far. So the distance from the interaction point, so we have to take into account the time of flight of the particles from the interaction point to the detectors. Here, for example, the time is like 58 nanoseconds to one side and 66 to the other. So, and this is already big
What
time.
is IP? That's impact parameter.
Interaction point.
Oh,
interaction point. And we take into account estimate how much the time of the light traveling to the photomultiplier, then the transit time of the photomultiplier, the signal travel from the PMT to one panel where there is some connectors, and then from the panel connected to the another panel which is connected to the front electronics. So you see, you can, for example, here I calculate the time of of the light travel here, the signal, and then the signal from these long cables up to 200 nanoseconds even. And then even the cables that are going like is zero 0.1 meters, which is already like 5 nanoseconds more or less. And then you have the calculation of how much time uh, it takes. For trigger detectors, this is crucial. Okay, so basic trigger logic in the trigger signals is basically a combination of and or combinations from the input signals, and that will define, for example, you can define, for example, specific triggers that are coming from a signal in uh, signals in, let's say, and FDD, and nothing here, and nothing in T0, but something in FDD, or something in
What
B0.
kind of collision would that be if you have signal in FDD and not in FD0?
This is, for example,
Because even ultra peripheral have FD0 signal, no?
ultra peripheral. No, ultra peripheral, you want nothing there, because you are looking for signals in Alice. You look for signals in muon arm here, and you are, for example, you are looking for events that are the muons in one arm. So did you have the muon arm here, but you want the cleanest as possible signal. So you expect nothing here, nothing here, nothing here, nothing here. And you look for this, like this is like better signal. Or even some, for example, some events that are diffractive physics, which you have some events in the inner barrels, and you get clean signals in this, or you or some others are you looking for signals in one side and not in the other. So there's different combinations for getting, for example, diffractive physics. And that you somehow design with this and or type of implementations on the trigger. There are other types, not only and or, but you also can have, for example, majority signals logic, which is you set some threshold of number of channels activated, or some specific charge that is measured by one detector. So you provide this trigger, or some topological patterns, which are
For
very
example, the
specific signals.
diffractive processes can be
Diffractive,
topological, that you have in one direction, but you don't have
yes.
in another.
Yes. Okay, triggers should be synchronous, of course, and they should provide a response every bunch crossing, and the logic has to be embedded in custom electronics to be as fast enough. So how do you get these trigger decisions? One way is to use lookup tables, which are tables which are stored in some memory, and this memory is a codification of the pattern of triggers that you expect from different trigger types.
Sorry.
Yeah, no problem.
They're bringing me a package.
Ah, okay. And what else? Yes, and this pattern that is stored in the memory is the brings at the end the output of the defined pattern. Yes. well, in this lookup table, you encode the the information that you expect. Yes. The other is use contents addressable memories. These are, where are these? This is a multi-bit memory cells which are packed with a comparator logic. And when this pattern occurs, presenting the logic address or index of the memory cell and appear to the output. Is also some memory type of getting the pattern. Also, this is actually the fastest, far as I know, which is a field programmable arrays, gate arrays, which is FPGAs, which is a high density chip with a lot of logic gates embedded inside, and you can interconnect between them. So in here you can implement some memories, even lookup tables or any logic, and this can be clocked up very up to gigahertz rate. So it's very fast. So no, this is what is used normally up to days. Also, there are digital to signal processors. They have similar features of FPGAs, but mhm. Well, this is more highly integrated and custom programmable. For example, they provide some custom programmable gate arrays also. This I
So
don't know how
what
to.
is the difference between FPGA and DSP?
This one it's integrate uh, what this does processing. So they have specific modules that do processing of digital signals. So they do calculations.
And the FPGAs are not able to do any calculations.
Yes, they can do, but they don't have specific modules that are meant for that purpose. So the FPGA are more flexible. You have to if you want some, you can program some digital signal processor in an FPGA, for example.
Mhm.
And digital processor has already some unit that does these mathematical calculations there. Like they are very efficient. So that's the difference. So, for example, this is how it looks, the trigger board of the Alice for the run tree. So there's an FPGA here, and this is how it looks. So it's crazy thing. So, but this is fast enough to provide clock at this at the interaction rate that one expect on from the LAC in Alice. So now we are seeing buffering. Uh, So well, we know that the cross section of one physics process it depends on the interactions per time. The probability depends on the interaction per time intervals, and this is well, this is instant luminosity and the cross section of this phenomena that we are looking for. And this follows some Poissonian distribution in terms of the frequency. So put something else in the. Oh. So so in the trigger and the readout has to cop this in this rate of the things that we are looking for. Uh, mm, mm, mm. Okay, and so we have constraints from the triggers. So this is mainly because of the capabilities of the processing time from the electronics, and for this we put some events in a buffer that can be later on related to a specific collision identification number or something like this. The advantage of this is that you can have further processing later on. And then and here the processing time plays an important role. So to satisfy the constraints in average, you have to you need to get this processing time to be larger than no the frequency that you can read.
Yeah,
Wait, is the
it's because you have limited number of buffers, so you
Yes.
cannot have the frequency so high that you run out of buffers, because then you have
No.
to stop the measurement.
No. Okay, yes, and well, and the average frequency that you can run is smaller than the one over the processing time, the average processing time of your system. Okay. So and then we have the dead time, which is the time where the electronics cannot cannot read out anything. So they have a finite time of reaction, and they need some time for establish their conditions to process another event. So the trigger level 1 is designed specifically to cope with this the higher rates as possible to minimize the dead time as much as possible. And well, and we can calculate this. Well, we have the dead time fraction, which is the time of an acting bunch crossing for which the trigger is not able to get information. This is luminosity. This is wrong. Where this is luminosity over the luminosity. So, and the cross section, what is this? Well, and your limitation for the cross section measurement is the frequency that you have, and 1 minus the dead time fraction of the detector over the luminosity.
I think that you had it correctly there, because this might be the luminosity, but FD is a fraction of time when the triggering is inhibited over the whole period of time, not luminosity. It's a fraction. It is just, it cannot have a unit, so it's supposed to be time over time.
No, because the frequency is the
It is.
cross section times luminosity.
Yes, so if you go back,
Yeah, but this is
if you do here, I don't understand why you have two lines there. What does that mean? Which one is in the numerator and which one is in the denominator?
This I can simplify, maybe put it like this, and then like this. So your frequency is limited by the
Yeah. So you need the FD to be a fraction of time over some different time. You need seconds and seconds, because you subtract it from 1, which is unitless. So
yeah, no, this is a fraction. This is unitless. A fraction of
yeah, but you cannot have luminosity there, because luminosity does not have a unit of second.
Luminosity is interactions, number of interactions per area per second, no?
Yes, so that is a different unit. So
let me think about it. Because
the dead time fraction is the time when you cannot read anything over the whole period of time that you're taking.
no, but this is not time. It's a fraction which is unitless.
Yes, so you need to have time over time. So you have seconds over seconds, and they cross out.
Yes.
So you cannot have luminosity in the denominator of the FD.
No.
Because this is a definition of the dead time fraction. So it is a fraction of time when the triggering is inhibited over the time when it is like over the whole period of time. No? Because what you have written here is that FD equals some time over L, where L is luminosity. And if you have that, you have seconds over the units of luminosity, which are not seconds, and you cannot cross them out, and you have a unit.
Let me see. We have this is area. Oh, it's not written. Right here. So we have cross section is area, and then we have luminosity, which is number of particles. Oh, it's too wide. It's too wide. So we have area, and then we have luminosity, which is a number of interactions. Number like this. Oh, number of interactions over time over area.
So you have number of interactions over time.
Over time. This is frequency.
Which is frequency, yeah. So you need here also to have unitless.
No, because this is frequency.
Yes.
And then you need unitless here.
Yes.
And this fraction is unitless.
That's what I'm saying, yes.
Yes.
But what you have written here, when you have changed this and you put their luminosity, what you're saying is that FD equals time of active bunch crossings for which the triggering is inhibited over luminosity. So you have time over luminosity, and it is supposed to be the FD. And that doesn't make sense because you wouldn't have a unitless FD. You would have second over luminosity.
And then, but like this is okay.
Yeah, the formula is okay, but the definition of the dead time fraction, there was over the lifetime.
Yes.
Yeah.
No, that was wrong.
No, that was okay. That was right.
Time? Why?
Because you are the dead time fraction.
Then how I had it, I forgot.
Yeah, just.
What happened?
I don't know. You cannot go back here for some reason.
Okay, it doesn't matter. So it was over the lifetime.
Yes. And that would mean that you have the dead time fraction, a time over time, and it is unitless. That would make sense.
Yes.
If you change it to luminosity there, you have dead time fraction, time over luminosity, and it is not unitless. It is not a fraction.
Yes, that's true. That's true. So the fraction over the punch crossing for which the trigger is inhibited over the
lifetime. Yes. It was live, like when it is alive. So not lifetime, but like what you had there was
what?
live
Lifetime.
time. Like it is alive. It is not dead time. It is a lifetime.
Okay, that's true also. Yes. Thank you.
Yes.
Pátek netuším, zítra je všude. Pátek, myslím, je normálně výuka. My teda tady nic nemáme, ale v pátek je normální den.
Okay. So, okay, thanks for the correction. Then, so the dead time of non-buffer system is calculated as the event n. The time of the event n follows, but the next event at some time. So the next event should be smaller than the time where the event occurred plus the time of the processing time of the detector. And well, this is the lowest timing that you can have for this specific detector, but you can improve the time, well, reduce the dead time by using buffering. So because you can describe the dead time using Poissonian distribution, where the mu is the frequency times the processing time of the detector. Then you can modify how the dead times reach the highest fraction. Yes. So for example, here when you have a buffer of 1, you reach very fast the dead time fraction. But when you increase, for example, here to 5 buffers, you reach this limit later on. For example, this is an example, a system with a processing time of 1 millisecond with 1, 3, and 5 buffers. So the time of 50% is reached at 1.7 kilohertz. And from 1 buffer, it's increased to 3.7. For 3 is 7.6, 5.7. And for 5, I don't know. I don't calculate.
It's 3.7 for 3 buffers and 5.7 for 5 buffers.
Okay. This for this for this. Okay. Okay. Then next part is the multi-level trigger system and event building. I don't think we are going to see event building, but this multi-trigger system is more or less like this. You have some detector, some pipeline here, and then you have a multiplexer that kind of order the information from here, and then no, wait.
The pipeline, like the two pipelines, is very different signal.
I think so. And then you have a trigger level that activates the multiplex. No, you have. If you see here, this small circle here means that it takes the negative logic. So when this is active, don't pass anything, and when this is inactive, this whatever is in the input goes to the output. So this is actually this is a multiplexer of just one. What it does is when
it either sends the signal or doesn't. It doesn't
Yes.
choose a signal from multiple.
No. It's basically sends or not.
But just
Exactly.
sends or doesn't send.
And then here you have.
And the circle means that it is like if nothing comes, send. If something comes, don't send.
Yes. And here have you some buffer for the higher level trigger, and then storage. Like it's one simple architecture. It's one of the many that you can have. Okay, this trigger has to be asynchronous. Oh, synchronous. Sorry, this one has to be asynchronous, and this second level can be asynchronous. They not necessarily need to be synchronous with the interaction from the experiment. Okay, what else is important here? So okay, normally this is not that precise. It's very rough estimation of some trigger pattern. Further algorithms can be added in this second level to clean up better. And here normally is custom electronics, and here can be is more is more common. No, it's easier to see that is well, it's more common to see that is use some conventional electronics because you don't need
That
that
specific.
speed like that fast systems. Okay, level 2 trigger. So in the level 2, typically, you provide tracks or precise momentum measurements. So you can provide a specific physics, physics signatures from detectors to do the selection, and can be slower. So that's and the combination of data fragments from various detector components is the task of the event builder. Well, this is a further task. So you combine the information for several detectors to get an entire event reconstruction. And that's it. Okay, this is trigger rates, and those can, well, this is very specific stuff. So these are like consideration of triggers design, which can be the various triggers can be designed for physical goals that can be optimized, such as the total recording rate experiment doesn't exceed its technical capability. So you can basically cut down somehow the amount of information to, because you don't have infinite storage. Yes. Um, Let me see what is also important from here. Okay, since later and the condition of data taking, well, okay, depending on the condition of the data taking, the condition of the trigger rates can change on time. So, and you could somehow adapt the trigger detectors or the detectors for different conditions. So, for example, if you have a PP or lead collisions, you have different type of conditions. For example, PP, you have a large multiplicity but lower rate, and PP, you have a higher rate but lower multiplicity. So trigger rate, all the triggers have to take into account this type of conditions. Take into account also the thresholds, logic that could be changed to adapt to these different conditions. What else?
The downscaler is when you have something that you want to measure, but it has high rates and you don't need all that information. So you just choose every nth, like 10th interaction to be detected, and the other ones you just discard because you know that they are more or less the same and you don't need that high statistics.
Yes, it's basically that. So you simply use do a cut on the number of events that you have. Um, okay, that's it. Then let's check some example from Alice how the different stages of processing. This, for example, here you see the raw data from the detector, which for LED you can have a 3.4 terabytes per second, which is very high. Then you can they implement some suppression factor of 6.6 to get a lower rate of information. And then there's a data reduction to doing online tracking, which do like some reconstruction to reduce even more the.
There is in the compression there is said that there is no event discarded during LED runs. How can you not discard any event and still have a cut from 3.4 terabytes to 500 gigabytes?
This it must be that you kind of do some. It can be like you do some formatting to the information, so you do have the raw data and you write it in some more compact format, like digital format, and you discard some, for example, noise that is there. For example, zero suppression, which is like events that had zero or some noise that the specific detectors you can actually calculate that. Okay, this is from the 16 channels, 3 are on and the rest is zero. And then you cut somehow the amount of information. But this is specific for each type of detector. So you can compress or discard some part of the information. And here also you reduce by reconstructing. So you get another data reduction. And during the storage, well, you get some data storage like for this 90 gigabytes per second. And then I think here there is some further processing that you get even smaller format for the when you do like full reconstruction of the event, so you have more compact data sizes. And here is how what part of the detector is involved on this thing. So here is the detector itself. Then you have here some common data unit that do this compression. Then you have this switching that I think here should be the event building probably. And then you have the processing with CPUs, the GPUs here. And then for other that I don't know what it is, but then you have the data storage and then for processing of the event building. Okay, this is okay. This is how it looks. The control trigger processor of Alice. There is here. Well, I will not go into detail, but here you have a for example, you have here inputs from the LHC clock, information from the clock of LHC. And then you have, you see, oh no, wait. So I don't remember exactly scope.
I think this part is a bit too technical.
Yes, very technical, and I don't remember because this is. This is the CTP, so it has a little bit, very a little number of inputs, but you have another like it's called LTU, which is the local trigger unit. Each detector have a trigger unit here. For example, this one provides the first trigger levels of trigger L minus, L1, and L2. No, or L0 and L2. And then there is a local trigger unit to provide further information to the CTP or higher trigger levels. And well, I think it's no sense to go into details here. This or again, the common redundant unit takes from some special link from the detector to this common redundant unit to do the to part well to this is wait. I don't know why it's not.
It is a trigger, so the detector.
The detectors get trigger
Question: the
information.
FGPA is a mistake,
FPGA.
and it is supposed to be FPGA, or is it? Yeah, okay.
FPGA. Okay, so here you have information further, like from the CRU to the detector, and from the detector to the CRU. And here you get some information back and forward, but the main information is from the detector to the cultural reality unit, so you get all the information from the detector. And here you have some processing that sends to the O square for processing or the CTP to take decisions. And well, this is an example of how it looks for the feed. This is very simple. Well, compared with other detectors, and this one is the main trigger of Alice. So you have two sides of the detector. You have the processing modules that Susana explained last time. So here you have the integration, the time information, and this connection is to the CRU, which is this thing here, to the processing. But also there is these HDMI cables that put the information to the trigger and clock module. So this trigger and clock module synchronize the data taking for each board, and also process the information from here to provide the different type of triggers to the CTP. So we have or A or C, vertex information, centrality, and semi-central triggers. So it's more or less, well, this in this in particular is how it works. So it's kind of not that complicated because it's levels minus. So it's just record or not, or something happen or not. Yeah. And I think we saw that with Susana, I think, in previous lectures. So we have constant fraction, integrators, and so on. So we skip it. And I think this also, here, for example, this is the PM board.
Yeah, this is what we saw last time.
And then, but we didn't saw this part. So here, the part I want to highlight is how the FPGA in this case process and what it does to send the information to the trigger units. For example, here in this case, this works with this has some bunch crossing counter. So internally this counts or it register every single bunch crossing which has an identification number. The orbits of the orbit identification of each bunch crossing that is crossing. In some even counters. Here also there is some buffers here and data synchronization for synchronization. And here this is the trigger and BC identification decoder. So this is some codification of the trigger based on these counters. And let me see. Okay, this If you see each of the boards send information here, and this trigger subsystem process the charge and timing, and this provides this also produce some logic inside and just send R the or A or C vertex, and that's it. Okay, you can see more or less here how it looks the logic here. So for example, or A is only any event in A side or in C side. This is any events that are in A and in C side. This is a sum. They can be different logic. For example, the central is if there is a threshold of total charge in one side and in the other. So it is only triggered when there is a when the total charge of the two detectors in both sides go over some threshold. And in this the same like this, but this is a different threshold.
Yeah.
And we are not going to do for this. This is just the time distribution over the different modules that the trigger or control module. I forgot the name.
Time and control.
Time and clock module. Time and clock module distribute the clock from LHC to the different boards that is from this detector. And then, for example, here. So we have, in this case, this is the feed detector. We have this electronic that is here and here in this overall scheme. And well, this is this part of the central, well, the processing part of the Alice system, and that's it. And I will not do this Atlas because there is another type of triggers that, for example, Atlas does a different thing. They have this only level 1 trigger and trigger level number 2 and some tier level. So they don't have, for example, I think, well, when I found this, they didn't have. I will talk in past because this is not updated. So they didn't have like continuous readout. So they were basically doing some triggers. For example, here you see that for the level 1, they have condition for calorimeter cluster, some clustering calorimeter, some calorimeter identification of jets or amount of energy, or some triggers on the muon detected in muon. They have some muon chambers. And I think this is too much detail. I think there is a part on the level 2. Level 2 here. For example, they have also what is for example, they have defined some region of interest building, and some region of the interest. So they produce a specific triggers, but mostly this is already some level 2, so second level of trigger, which is this thing here. So, and this is supervised or done in a CPU. So for in a farm of computer, it's already not a custom electronics, so they can work slow here in this part. And event filters. They have this event filter, so they have a further selection after the event building, and after that they have storage. So they store just after they have build events.
An event, then do some selections.
Selection and then store. Yes. So that's a different architecture. Well, that's all the point of these slides, and this is how it looks technically. So. For example, here they have this level 1 with the different selections in level 1, the different selection on level 2, and the even filters, and the different rates that they have on each stage. And this is, for example, here is how they define the different level. Well, these legends, how they define all these things. But that's it. Okay. Okay, what time is it? Oh. Okay, so more or less.
Yeah, sure.
We can finish the lecture here and we continue with digital next time because
we can continue. I'm just gonna check.
okay. So stop.